Welcome back. We're in chapter 14 on acids and bases, and we're now to 14.6, which is the pH scale. A lot of people recognize what a pH is, that pH has something to do with how acidic it is. The H, if in pH, is per hydronium. Okay, so the pH is basically, do I have more hydroniums or less hydroniums? There is something a little interesting about the pH scale, and there's some real math involved in this, kind of algebra 2 kind of math. So it's not as bad as it might seem, and I'll get to it in just a second. So let's look first of this generic uses of pH. A pH scale ranges from acidic, which is at ranges from 0, 1, 2, 3. Those are acidic solutions, to a 14. And a 14 would be a very basic solution. So remember acids and bases. If something is more acidic, then it has less bases in it and more acids. If it's more basic, it has more bases and less acids. If you have equal numbers of acids and bases, you have a neutral solution, and that's at 7. If you remember, water breaks apart into equal amounts of hydronium ions and hydroxide ions. And so you have just as much acid as you have base. And if you were to take the pH of water, you would have a reading of about 7. If it were pure water, you would have a reading of exactly 7. So you're going to see that acids and bases are very prominent in everything that we use, most of our tools. All of our cooking has acids and bases in it. If you remember in the definition of Arrhenius acid, even the Greeks, the ancients, saw that acids were very sour, like lemon juice or orange juice, that there was a tang to it. Vinegars, things like that were very kind of tangy, that was acidic. Basics have a more bitter taste. Even soaps, things like that you can make out of bases. So all of the range of products that you would use for your house or for in industry and in your cooking have a basic or acid range. Your blood has a very specific acid range, and if it gets even the smallest amount out of line, you'll die. Okay, if your blood becomes a little too acidic, you get something called acidosis, and you die. If it becomes just the tiniest bit too basic, you get something called alkalosis, and you die. I think it's called alkalosis. I might have made that up. In any case, look at this very poorly done schematic of acids and bases. You have things like your stomach acid has an acid of 1.6. You have soft drinks, which have an acidic range of about 3. Orange is a little more, 3.5. Once you get up into coffees and milks, and then neutral at 7. This is where pure water is. Anything towards this side, and you're going to have bases. So anything past 7, and you have a bases. Acids will turn litmus paper red, and so they're usually shown as red. Bases will turn litmus paper blue, and so normally bases have an appearance of blue in a schematic. So seawater is a little more basic than pure water, then ammonia, which is NH3 if you remember, and then eventually bleach, and then drain cleaner. So Drano. So there's Drano and hydrochloric acid whenever you're making methamphetamine. Please don't make methamphetamine. It's a very bad use of your chemical knowledge. Plus, it completely kills you. That is poison. Never, never eat that. So, going on, you can figure out a pH of a solution with a lot of different means in the lab. We're going to take some cheap paper that has a little bit of an organic dye in it, and it will turn different colors depending upon the pH. So if you have a pH that if you put a solution in dissolved in water on that paper, you will get various colors of that paper determined based on the pH of that paper. And we have some in the lab. We also have a pH meter. We've got a pH meter in the lab that we can use to detect the pH of a solution. Okay, so there's various indicators and ways that you can do that. Here's the math. I'm going to tell you, first of all, that this is scary math. I remember being scared by this, but the math that we're actually going to use is so simple that it's a George Washington's white horse type of question. Okay? Let me give you the definition of a logarithm. A logarithm is what power do I need to raise a number by? Okay, I'm sorry, what power do I need to raise the number 10 by to get a number? If you give me a number, what do I need to say 10 to the what equals that number? Okay, if you can give me a number and I can give you the power that you raised the number 10 by to get the equal amount, then I've given you its logarithm. Okay, so watch this. Easy problem. What number do I need to raise the number 10 by to give you 1 times 10 to the negative 4? Well, it's negative 4. Negative 4 is what I raise 10 by to get you 1 to the negative 4. All right? When you are finding pH, pH is defined to be the negative logarithm of the concentration of the hydronium. So you're going to look at the hydronium, whatever its concentration is. Remember, 1 times 10 to the negative 4, this would be acidic. This is an acidic solution. What is its pH? You're going to look at the exponent, ignore the negative, and this is going to be your pH. 1 times 10 to the negative 4, the pH is 4. If you recall that pure water, the concentration of hydronium is 1 times 10 to the negative 7. So the negative logarithm of 1 times 10 to the negative 7, or what number do I need to raise 10 by to get 10 to the negative 7? Well, the number would be negative 7. I'm going to take the negative of that. The negative logarithm is the negative of that number, and the negative of negative 7 is 7. So rather than deal with a very small, tiny number, I'm dealing with a big number, 7, that shows me that I have a neutral solution. So anything at 7 is neutral. Anything less than 7 will be acidic. Anything greater than 7 will be basic. Okay. Another word for basic is alkaline. It's an older word, but it's still the same idea. Basic and alkaline are the same. Now, a little bit of fine tuning. If you have a coefficient of 1 times 10 to the negative 4, this is a coefficient to the ones place. There's one significant figure here. You're going to have to give me 1 decimal after the pH. So instead of just saying it's 4, the negative log of 10 to the negative 4 is 4. If it's 1 times negative 10 to the negative 4, I'm actually going to give it 1 decimal place, 4.0. If I have 2 significant figures in the coefficient, in this case 8.0, then I'm going to have 2 decimal places, and likewise, and so on. Okay? Here's where it becomes the tiniest bit harder, but it's still really easy on a calculator. If I have 1 times 10 to the negative 4, I can do this in my head. What number do I need to raise 10 by to give me 1 times 10 to the negative 4? Well, it's negative 4. Okay, so I take a negative, and I've got 4 as my log. But if I have any number like this, 8.0 times 10 to the negative 6, all I'm going to do is put this number in, push log on your calculator, and then push the negative or change the sign, and I'll have the pH. That's how you're going to do it. You're just going to do it with your calculator. So, everything is based on the concentration of acid. So you take the concentration of your hydronium ion, whatever that concentration is, hit the log key, and then change the sign from positive to negative or negative to positive. And then that is your pH. You adjust the number of significant figures to the right of the decimal based upon how many coefficients you had in the original concentration. So here's an example. Find the pH of the solution of hydronium of 1.0 times 10 to the negative 3. Okay, I can do this in my head, right? Because this is a 1. I can do this. The number that I raised 10 by to get 10 to the negative 3 is negative 3. And now I change the sign from negative 3 to positive 3, and I get a 3. Okay. If I otherwise, I take this number, 1.0 times 10 to the negative 3, put it into my calculator, push log, okay, which is a base 10 log, and then I change the sign. Now, you're going to get a number after 3 on your calculator. How much do you write down? Based upon what your original concentration was. If you have a 1 or a 1 digit here, you're going to have 1 digit after the decimal. If you have 2, like in this case this is 2, then I need two decimal digits after it. So it's your acidity or your pH level would be 3.00. Okay. Now, they're being sneaky. What if they don't give you the concentration of hydronium, but instead give you the hydroxide concentration? We had this problem before. If you remember, K sub W, the constant for ions that breaks apart in a glass of water when you set it on the counter, is always 1 times 10 to the 14. So 1 times 10 to the 14, negative 14, equals the concentration of hydronium times the concentration of hydroxide. Okay, so you're going to have K sub W, which is always 1 times 10 to the negative 14, is going to always equal the concentration of your acid times the concentration of your base. Okay, it's going to have that all the time. So if they give you the base and they don't give you the acid and they make you do an extra point because they're just trying to drive you crazy, then all you're going to do is put it in this formula first. 1 times 10 to the negative 19 equals something times what they give you. Solve for the acid. Okay, now you've got the concentration of the acid. Put this number in, 2 times 5 times 10 to the negative 10. Put it in your calculator. Hit the log key and change the sign. And you're going to end up with a pH of 9.6. Okay, we'll do a lot of these examples in class. That's nasty. I hate it when they do OHs. Okay. Now, if you don't do a pH, but you do a POH, that's really the same as doing the acid, only you're not measuring the acid, you're measuring the base. Okay? So instead of, remember the pH is the negative log of the concentration of hydronium. Well, the POH is going to be the negative log for the concentration of hydroxide. So, big deal. Just put that number in instead. It's no big deal. A POH is simply going to be how basic is it. So if you have it's going to be higher values, has high OH values with low OH values. Okay, so the higher the hydroxide. Let me say this so I don't confuse myself or you. Has high POH values with low OH values. Okay, so the lower this is, the more basic it is, and the high acid. So don't worry, just put the concentration of OH in, and take the negative log, and that'll give you your POH. Okay, if you're trying to find the pH, you're putting in the concentration of the hydronium ion, and taking the negative log of that, and it'll give you a number. Okay, again, it's just to drive you nuts. Here's an example. Calculation of POH. Calculate the POH of a solution that has a pH of 8.35. Well, that's easy. Everything adds up to 14. Whatever the pH is, the other adds up to 14. Because because there's only 14 in a pH scale, and if you've got a pH of 8.35, what's left over after you get to 14? So 14 minus 8.35 is 5.65. So if you have a pH of 8.35, 8.35 plus what equals 14? That's your POH. Okay, that's all it's doing. Calculating hydronium from pH. All right, now this is essentially going backwards. If you're saying if your pH is the negative log of the concentration, then how do you go backwards? Okay. So, if you remember, the pH is going to be the negative log, which is the exponent. What is the exponent? What power do I need to raise 10 by to get you a certain number? So all you're doing is finding out what is here, what is in the exponent, and that's your concentration. For instance, if you have a pH of 3, then remember it's a negative 3. So you're taking the negative 3 and changing the sign, and you ended up with 3. That means that your concentration is 1 times 10 to the negative 3. Okay, we'll do some of these examples. This gives me a headache. Calculate the hydronium for a pH of 8. Okay, so we've got 8.0. That means that I've got that I'm going to have one significant figure. Okay, so it's going to be 1 times 10 to the something. Well, my pH is going to be this thing. So if it's 8, the last thing I did was change the sign, so I need to change it back to negative, and then that's the exponent. You're looking for the exponent, so the exponent is the 8. All right? I need you here. I could teach you if I just had you right here with a blackboard. So adjust the number of significant figures in the coefficient. If it's 8.0, then that's showing you that it's 1 times 10 to the 8. If it's 8.00, then it's 1.0 times 10 to the negative 8. Essentially what you're doing backwards when you're going the other way. Here's the last, and this is an easy idea. If you have a 7 out of 14, between 1 and 14, 7 is the middle. It's neutral. If you're looking at the pH, anything higher than the 7 is going to be an acid. Okay, anything higher than the 7 is acid. Anything beyond higher on this chart, going up to 0. So any low number like a 1 is going to be very acidic. Any high number up to 14 will be basic. 7 is middle. Up down to 0 would be very, very acidic. Like stomach acids, like 1.6. Anything high up here like 14 would be very basic. That's like drain cleaner. pOH is exactly inverse. So anything that's high, the high numbers are very acidic. The low numbers are very basic. So these are inverted of each other because these things are inverses. The pOH and the pH and the pOH are exactly opposites. We need a lot of work, and this might take a couple days to play with in our paper. So ask me questions as you have them, and I'll see you in class.